Welcome back to the lecture series on EC206 Computer Organization Module 6. Today we will be talking about replacement algorithms. Now replacement algorithms can be studied for cache as well as for a virtual memory system. Let us first consider replacement algorithms for cache memory. So caches we know are of three types: direct map, set associative and fully associative caches. Let us look first at the direct map cache. Each address maps to a unique set and block. Okay, so each address in the main memory maps to a unique set and block in the cache. So if that set is full, when new data is loaded into the cache, then the single block in that set is replaced with new data. So there is no confusion. Now in the cache there is just one block which is sitting inside the each of the sets. So when the particular set is full and when new data has to be loaded into that set, the block in that set is replaced with the new data. Now coming to set associative and fully associative caches, the difference here is that instead of a single block in each set, there are several blocks in each set. Okay, so if the set is full when new data is loaded, the cache must now choose which of these several blocks to evict. Meaning of evict is to replace. The data in that particular block will be replaced. Which block to evict when the cache set is full. So here there was no problem. There was only a single block and the data in that block will be replaced. Now here there are several blocks. So when a set is full and new data has to come into that set. Okay, what is the meaning of set is full? All blocks have got data. So when new data has to come into the set, the cache must choose which block to evict when the cache set is full. So one of the policies that is used for this is called the LRU policy, the least recently used policy. So the best choice is to evict the least recently used block. This is based on the principle of temporal locality. Just to revise that, temporal locality means, in simple terms, if the processor has used a particular data now, it may need it immediately in the near future. So that is the principle of temporal locality. So looking at that principle of temporal locality, the block that has been least recently used, okay, that we can choose to evict, and that is the foundation of the LRU policy. Now consider as an example a two-way set associative cache. How is this LRU policy implemented in this two-way set associative cache? This cache has a use bit U. It indicates which way within a set has been recently used. So U can be 0, U can be 1. Based on that, it will tell us which way within a set has been recently used. So each time a way is used, the use bit is adjusted to indicate the other way. Okay, each time a way is used, the use bit is adjusted to indicate the other way. That is show that the other way is the one that is least recently used, and that is the other way that has to be, the block in that has got to be evicted. Now, suppose we have set associative caches with more than two ways. Or we are looking at the problem of, let us say, fully associative caches. So the problem of tracking the least recently used way now becomes more complicated. You can't use a single use bit. Okay. To simplify the problem, the ways are divided into two groups itself. Alright, the ways are divided into two groups. The use bit U now, instead of indicating which way is the one that is least recently used, now it indicates which group of ways is least recently used. Okay. So when a replacement is required, the new block replaces a random block in the least recently used group. In the previous case, in two-way set associative, the new block replaces the least recently used way. Okay, the block in the least recently used way. Now here we don't have a least recently used way. We have a least recently used group of ways. Okay. So when a replacement is required, the new block replaces a random block in the least recently used group of ways. So this is not really an LRU policy. This is called a pseudo LRU policy. Now looking at replacement algorithms in virtual memory systems use two techniques. One is write back, which we have talked about in write policies video lecture. The physical page is written back to the disk or the virtual memory only when it is evicted from the physical memory, unlike the write through policy. Okay. And another technique that is used is an approximate least recently used policy. Now, two terminologies that we use in this case are swapping. Swapping means writing the physical page back to disk and reloading it with a new virtual page. That is, when a physical page has to be evicted and a new virtual page is coming there, the word that we use is called swapping. And swap space, the disk or the virtual memory, is called the swap space. Now, to support these replacement policies, what are the replacement policies? Write back and approximate LRU. Each page table entry contains 2 additional status bits. We had talked about page table in the previous lectures. So now there are 2 additional status bits for each page table entry. They are called dirty bit D. When a physical page is swapped out, it has to be written back to disk only if D equal to 1. We had talked about this D in terms of write back policy when we said that if there is a change, that is if the physical page has been written into by the processor, then what is there in the physical page and its corresponding page in the virtual memory now are different. Okay, so the dirty bit D is used to indicate that. Now, if there is a change in the physical page, then D is made equal to 1. So, when a physical page is swapped out, only if it has been changed, then which is indicated by D is equal to 1, then only it has to be written back to disk. If D is equal to 0, then there are identical copies in the physical memory as well as in the virtual memory. So, that is the role of the dirty bit D. Now, there is also a use bit U. U is set to 1 if the physical page has been accessed recently. Okay, just like we had seen for the cache, U is set to 1 if the physical page has been accessed recently. Now, the number of physical pages is very, very large. So, an exact LRU policy implementation is impractical. So, the operating system approximates, that's why it's called an approximate LRU policy. The OS approximates LRU periodically by resetting all the use bits to 0. After some time, all the use bits will become 1 if we don't do anything about it. So, periodically, the OS resets all the use bits to 0. Okay. And upon a page fault, now what is a page fault? Now, if the processor is looking for data in the physical memory, if it doesn't find it, then it is called a page fault. Then it has to go to the virtual memory and access the data and brings that particular page into the physical memory also. So, upon a page fault, the OS finds a page with U is equal to 0. That is, it has not been accessed recently, and that is the page that is swapped out. It does not replace the least recently used page. It replaces one of the least recently used pages. So, because of these points, that is why we call it an approximate LRU policy.